Hello, Astronomy on Tap. It's great to be back. So I'm Dr. Boom, also known as Dr. Chris Lindner. I did my PhD here at UT Austin. Nowadays, I actually do education research at a company called Civitas Learning here in town. And I'm going to talk about my favorite topic, which is stars blowing up. It's what I did my dissertation on, and we're going to see some of the simulations I did as part of that and learn some stuff. So let's start real basic. Some stars blow up. And we call these things supernovae. We observe these by basically seeing stars that we probably never even noticed before. When stars blow up, they can be so bright that they'll outshine their entire galaxy, outshine hundreds of billions of stars for at least a brief moment. And so sometimes we capture these things just by accident. So if you take a look at that middle picture there, we're basically seeing, oh, okay, there's this spot in this galaxy that really was nothing there for a while, couldn't really see anything. And all of a sudden there's this giant bright spot here. That's a star blowing up. And so sometimes we catch these by accident. We just happen to be looking at a galaxy. Nowadays, we also do these surveys where we have robotic telescopes just scanning the night sky looking for something that wasn't there before. And if they find something, they signal all the other robotic telescopes and say, hey, come look at this spot. It's really interesting. So they're super, super bright. We discover hundreds of these every single year. And in the Milky Way, we think there's going to be about one every 50 years. But luckily, these guys are so bright, you can observe them from across the universe. They're some of the most distant objects we can observe because they're just so darn bright. They also leave behind really cool corpses. We call these supernova remnants, which are these beautiful things that you see here. So after these have exploded, all that stuff that exploded starts running into the gas and dust and all the other stuff in space surrounding that star. All the remnants of the star just start bumping into it and make lots of pretty colors. These are often observed in lots of different wavelengths, so these pictures are actually mixtures of radios and X-rays and visual and everything in between, and lots of people spend their time studying what the heck is actually going on with these guys. Like I said, these guys can be really bright, and if they're in their own galaxy, you can actually see them with our naked eye, potentially. One famous example of that is a supernova that happened in 1054, where basically lots of different societies were able to record that, yeah, there was this thing so bright in the sky that you could see it during the day. It wasn't there before. It may have even been brighter than the moon. There's a questionably apocryphal story where this might be a Native American drawing of that. I choose to believe it because it's kind of cool. We don't really know, but that would be the moon, and it's like a hand distance away from where the star would be. But in any case, other societies recorded it back in 1054, and now if we look there today, we get this beautiful supernova remnant called the Crab Nebula. So these guys are really cool, and they give us another way to kind of study what the heck is going on with these stars that are blowing up. So what types of stars blow up? Well, it turns out lots of different types of stars can blow up. Stars like our sun typically will not blow up on their own. In fact, our sun is probably not going to blow up. What'll happen with it is it's about 5 billion years old now, and another 5 billion-ish years, it'll kind of puff up, and then it'll contract, and then it'll cool off. And it'll just be this sad little white dwarf that just cools off and cools off and cools off till the end of time. But if our sun happened to have a friend that could either dump a bunch of material on it or maybe run into it, then it can make an explosion that we call a type 1A supernova. And these are one type of supernovae that we can observe. I will not be talking about these guys today, but they are actually very important to astronomy. And if you've been to other talks here, you've probably heard us talk about them before because they're a very interesting type of supernova. The type I will be talking about are for bigger stars, stars that are 8 times the mass of our sun, or really I'm going to be focusing on stars that are like 20 to 40 times the mass of our sun. And these stars, they get to blow up all on their own. They don't need a companion to donating material. They've got plenty of material themselves. They live for a very short time. So you see, I said the sun will live for 10 billion years or 5 billion years more from now. These guys only live for 10 million years, which is kind of crazy because they've got way more fuel than our sun does. But as it turns out, they burn a lot brighter than our sun. They burn through that fuel a lot faster. And at the end, they just blow themselves up. And so a lot of my work has been understanding why some of these stars blow up. And so I'll share some of that with you today. I won't talk about this class at all before, but there are some thoughts that there might have been really, really, really big stars out there at some point in the universe, stars over 100 times the mass of our sun, and they blow up in a totally different way. But basically, there's lots of different ways stars can blow up, lots of different ways people study them, but we're just going to focus on a very specific type today. So why do these like 20 to 40 solar mass stars, why do they blow up? Well, these stars, they run into a problem in their lifetime. Basically, stars are always in this competition of they have to support themselves against their massive weight. They have all this gravitational pull. They just want to collapse on themselves. And the only way they can keep themselves puffed up is by generating lots and lots and lots of energy. And the way they do that is through a process called nuclear fusion, which is basically just taking light elements and turning it into heavy elements. So you take, helium and you turn it, or you take hydrogen and you turn it to helium, and helium can combine with some other stuff and make you some nitrogen and some carbon and some oxygen and maybe neon and magnesium. And all these processes generate more and more energy, and they keep the star supported. But it turns out once you get up to building iron and elements heavier than iron, it's going to take you more energy to get to fuse iron than you'll get out of it. So all of a sudden you run into this problem where the star has been supported by all this energy it makes by building heavier and heavier elements, and now it can't produce that energy anymore, and it's going to start to collapse, and collapse very, very quickly. And so what happens in these stars is they live out their 10 million lives, glowing very brightly, building heavier and heavier stuff, and then all of a sudden they start making iron, and in a matter of minutes their core collapses, and the star collapses, and somehow it blows up. So how does it blow up exactly? Well, we think that core will collapse into a neutron star and potentially even collapse into a black hole inside the center of this star. And now if you watched the 2009 Star Trek movie, you might remember that a central plot point was that in that movie, there was a star that was going to blow up, and they were going to shoot a black hole into the center of it, and that was just going to suck the star up. And that's a pretty natural assumption to make, right? Like, black holes like to eat stuff. They're just going to suck it up. There'll be no star. Everybody's safe. Everybody's happy. You don't have a star anymore to keep your planet warm, but who cares? Whatever, it's okay. But as it turns out, that's totally wrong. We actually think that a lot of these supernovae are driven by black holes eating them from the inside out. And stuff doesn't just fall straight into the black holes. There's actually a lot more complicated physics going on inside of these guys. So this process where black holes are eating things is called black hole accretion. And so there's this idea that, like I said, they assumed in that movie that material would just fall straight into that black hole. But as it turns out, most stars are rotating, and as a result, as material will fall on towards that black hole, it will probably form sort of a disk around it, a rotating disk of material, which we call an accretion disk. And so it forms sort of this donut of material around it. And inside of that disk itself, all sorts of crazy physics happen. Things get really hot. Things start rubbing up against each other. These sort of winds start getting generated. These crazy jets get shot out of it at nearly the speed of light, just jets of material that almost fall into the black hole, but the material gets shot out away before it can actually fall in. All sorts of crazy, crazy stuff happens right near this black hole in this accretion disk. So now's a good time to put on your 3D glasses. The red lens should be on your left eye, so you've got it backwards otherwise. Red lens over your left eye. All right, and so what I'm going to show you is a simulation I did of black hole accretion. And basically what you're going to see here is material falling into this black hole. And then what you're going to see is that this black hole is actually going to generate a bunch of jets that are going to shoot out material at very, very high speeds, very, very close to the speed of light. You're also going to see these wonky little lines in this visualization. Those are magnetic field lines. Not going to talk about those today. If we learned anything from Insane Clown Posse, it's that magnets are really complicated, so let's just not even go there. But all right, show this here. All right, so we're seeing material starting to fall in. The black hole, material's going to start falling in. Right now we're starting with this donut of material around this black hole in the center. Material will start to fall into it. We're going to start to generate these sort of jets. And boom, you see this big explosion of material being shot out in this jet here. And then you see these jets coming out at you, these astrophysical jets. Again, material moving out at very high speeds. Now, most of the material in this accretion disk is falling into the black hole. Just a very, very, very small percentage of it gets shot out in this jets. But these jets have lots of energy in them. They're moving at very high speeds. And there's also winds that can get driven off this disk, basically material that just gets really hot on the edges of the disk and just flies off and things like that. So there's just lots of energy being generated here. And even though most of that stuff gets sucked into the black hole, there is some stuff coming out that didn't quite make it into the black hole and gets shot out away from it. And that's what you're seeing here. And then, yeah, again, the magnetic field lines, don't worry about those, too complicated. All right, and this isn't just theory here yet. You can take your glasses off. I'll have one more picture at the end that's in 3D. So this isn't just theory. This is actually something we observe in nature. Very often we observe these in the supermassive black holes that are in the center of galaxies. Basically, in these black holes, they often have these jets, and that's what you're seeing here. These are two different galaxies, Centaurus A and M87, not the band, but the galaxy. And you see that there's these jets here of material that are being shot away at very fast speeds. We get to observe those, and we say, yeah, that happens. And we think that happens with smaller black holes as well, and we observe those in different ways. Oop. But we've got this problem. These black holes in these stars are eating these stars from the inside out. And so all of this cool physics that's happening is happening way down deep in the star, way buried in there. And so we can't really observe all that cool stuff that's going on because there's just layers and layers and layers of star blocking our view of these things. We see the explosion, but we don't get to see the thing that's actually driving the explosion. So how can we study this as astronomers? Well, that's where theorists like me come in, and we say, okay, well, we know the laws of physics, and we can kind of figure out what we think might happen when you have a star in this sort of situation. Now, it turns out that this takes trillions upon trillions of calculations, and I'm not going to sit there and do it by hand. So instead, we use computers, or really supercomputers, to do it for us. So we take the basic laws of physics, basic things you know about gravity and how fluids work and magnetic fields and all these sorts of things. We take these basic laws of physics and we encode them into a computer program, and then we run them on many, many, many computer processors, thousands of computer processors for thousands of hours, and we come out with this simulation of what we think is actually happening in nature. And then after we have this simulation, we can then probe our simulation, look at the results of that, and see, did we actually match what we see on the other side of nature? Did we actually get the right results? So what I'm showing you here is sort of our model of what we think is going on in this explosive process. And I'll show you a simulation, one of the simulations I've done of this. And basically the idea is we think that you've got this really big star, and then this accretion disk, like you saw before, this is a slice of the star, so kind of a 2D slice of the star. But you've got this little accretion disk that makes up just very little of the mass of the star, but the star itself is collapsing down in this accretion disk and feeding it, and then lots of energy gets generated in this little accretion disk. And then that energy gets carried out throughout the star, and that energy can then drive the explosion that we see. And even though most of the stuff ends up falling into the black hole, enough of it gets out, and enough energy comes out that we see a really cool explosion. So the video I'm going to show you here is from a simulation. It's actually zoomed in so we can see just this little region around the accretion disk here. And what you're going to see, this is density here. So basically the more red colors are the dense material, and then as stuff falls in, it'll get yellower and greener and bluer as it gets less and less dense. But what you'll see is the star starts to collapse, things just sort of fall in for a little bit, and then all of a sudden this accretion disk forms, you get a shock wave, and you get some crazy stuff happening. So again, material falling into this guy, we form this accretion disk, we get a shock wave, we get this disk with this convection going on, stuff getting carried out further and further in the star, and we think this could drive an explosion of the star itself. This next video I'm going to show is a little bit more zoomed out, so you're actually seeing the surface of the star here. Again, we were zoomed in before just where that accretion disk is, but you're going to see the surface of the star here. I'm also showing something called entropy. Just think of it as like this is where all the energy is getting generated in the star. And what you're going to see is very, very, very close in the center where this accretion disk is, lots of energy gets generated, but then convection carries it out and sort of drives this explosion as this black hole is being fed inside of this star. So here we're just seeing material fall in and fall in and fall in. And then all of a sudden we see, okay, there's our shock wave forming. Our accretion disk is just a little itty bitty thing in the center here, but it's just all of this energy is being carried outward and outward and outward and driving this explosion that we see. And so all this stuff that looks like paint mixing or something like that, it's all of this energy that gets generated down here, and it's just got to get out, and it's just got to cause this explosion. And even though most of the material is still going to end up in our black hole, enough energy gets out, enough material gets out that we get to see really cool explosions as a result of this. So how do we actually trust this? I've done these simulations. It's a bunch of computer stuff. How do we actually know this is a real thing and I'm not just making it up? Well, one way we do that is we try to match what we observe. And we know that these things are really, really energetic. And I'm not going to go into the numbers because they're numbers that are bigger than any human can fathom, but there's a lot of energy that gets generated in the supernova. And basically, in our simulations, we find that, yeah, the energies we get pretty much match what we see in observation. On top of that, we expect that you're going to make all of these new elements in the supernovae, more nucleosynthesis going on, and the stuff that we generate in our simulations matches that pretty well. There's also a whole other phenomenon that I'm not going to talk about, but gamma ray bursts are another crazy explosive super energetic thing that happen that are associated with this type of supernova, and we match those observations pretty well as well. Which gives us some confidence that, hey, like, we just put in some laws of physics, we guessed at what we think the star is like, and we got out the real results you see in nature. So that's pretty cool. But can we really trust these simulations? Yeah, I don't know. I mean, there's lots of different models for how stars blow up. There's lots of ideas about why. Lots of other people are running these simulations. We had to make lots of different approximations, lots of different guesses. We could have done this more refined, more detailed, whatever. And you can always get better and better. And to me, I think this is awesome. It means there's more work to be done. There's more science to be done. There's more work for the next generation of astronomers to kick off and try to find out more cool things about how these stars are blowing up. So on this last slide here, I got one more 3D image for you. It's an artist rendering of a supernova remnant. Unfortunately, we can't actually take these pictures in 3D, but this artist painstakingly went through, mapped out the locations of all these stars, and also made a 3D model of the supernova remnant and came up with this really cool little 3D picture of it. But in conclusion, lots of different stars can blow up. The biggest stars, some of the most energetic explosions we see, we think might be driven by black holes eating those stars from the inside out. The black hole actually forms an accretion disk that drives that explosion via these winds and these jets and these other things that you saw there. And we can probe these explosions both by looking at them from the outside and doing simulations from the inside and trying to meet up in the middle and see where the truth is. So all right, that's all I got. I'll take any questions.
Thank you, Dr. Boom. So, right there.
The convection videos that you showed, were they real time?
The convection videos that you showed, were they real time?
I think those ones in particular are sped up about 10 times. So this whole process takes a few minutes.
Believe.
Yeah, thousands and thousands of years. I mean, I don't know how long they're observable. Tens of thousands of years is what I'm hearing from him. So yeah, something around that, yeah.
Astrobit is the current PhD supernova expert, so he's off on the side.
I'll put on pretty 3D video too while we talk here.
Yeah. For those that missed, those that came in late. Down in front.
What are the odds of a supernova happening near us, and what will happen?
So, I mean, depends on near, but probably, they're pretty rare for anything to happen near in our lifetime. I mean, again, there's one every 50 years, we think, in the Milky Way, but there's 100 billion stars in the Milky Way, so the chances of one of those being really nearby is pretty rare in our lifetime or whatever. On top of that, if it's not that close to us, it's probably not going to affect us, even if it's one of our nearby neighbors, with the very little exception of if that jet that black hole produces is pointed right at us, that would be a bad day for us. That would be a real bad day. But that's thought to be pretty rare for that to happen. We're probably fine. Don't keep yourself at night thinking about that.
Are there any up in the balcony? No. Your chance. Oh.
Yeah. You had mentioned earlier that I believe it was the Crab Nebula that was observed in 1054. You said a lot of these occur in a blink of an eye, a few seconds type. I think that one was actually documented for the last year.
Right, yeah, it could be seen day and night. So they go on for a while, but the peak brightness is only a few seconds, and then it decays over time. But then that one was so nearby that we could see it for a very long time.
And just behind.
Yes. So the heavy elements are being made, iron and above. How high does it go? I mean, I've heard of plutonium, stellar plutonium.
Yeah, I mean, all of those crazy heavy elements, pretty much all of them get created during the supernova process. So it's kind of a weird thing. So during the star's life, it needs to make these elements to keep itself supported. But as it dies, it doesn't really care about that anymore. And you get all sorts of crazy physics going on where you start building these elements that don't generate energy, but everything's just so hot and so energetic and so crazy that you build all this heavy stuff, including plutonium and things like that. So yeah, when you're talking about radioactive elements, for sure, I mean, those are generated in explosions like these, get shot out, and then we power our nuclear plants with them. So the question is, can we predict supernovae at all, like observationally? Not really. I mean, the problem is, like, we can look at stars in our galaxy, which we think will blow up in the next, say, 100,000 years, or maybe even, tens of thousands of years. But that's, that means that we probably won't get to see them in our lifetime. We can't get so accurate that you could say, like, this star is going to blow up in my lifetime. Probably not going to happen. We can't really predict them, unfortunately.
And with the beard, yeah.
So in the supercomputer modeling of this view, are you trying to come up with like a single equation that you can run this through and it's wondering the output, or is it running things through a series of physics equations?
Yeah, it's a series of physics equations. It basically divides the star up into like a few million little tiny boxes where it tries to solve physics in just an itty bitty little box, and then says, let's do that a million times, and then let's do that a million times that million times. You just do that over and over and over again, and then you get these simulations. Yeah.
It's really simple like that.
Yeah, just real easy.
Yeah.
Do we see the supernova every 50 years? Like, I've never heard of supernova.
No. So yeah, that's actually much less than the observed rate. The question was, we have these supernovae that occur every 50 years. Why don't we see them every 50 years happening in our own galaxy? And the answer is, yeah, we think most of them are probably obscured by dust. They're somewhere in our disk. There's just too much crap in our way for us to actually be able to see them, unfortunately. So most of the ones that happen in our own galaxy, we think go unnoticed. Now, I'll also say that we don't fully understand that rate and don't know how accurate we are in that. So there's other questions there to be answered. But yeah, we think that most of them are just being obscured by the other stuff in our galaxy.
Yeah, in the back.
If they happen every 50 years, does that mean there are every 50 years worth of black holes in our galaxy?
Well, not all supernovae form black holes. In fact, most of them do not. So no, there probably are not that many. The vast majority do not. This is, again, just a very specific class, and it's actually kind of an unsolved problem as to what masses, what types of stars we think actually form black holes. There's a lot of people out there who argue that most of them just form neutron stars, which are pretty dense and pretty crazy like black holes, but not quite the same thing. So we don't think you're forming nearly as many black holes as that rate would imply.
Okay, well, with that, let's thank Dr. Boom again.